Hi, everybody. This is Mrs. Gladfelder. When we start today's lesson, I want you to consider the question that you see before you here. What is the difference between intramural and interscholastic sports? Now, I know that might seem like a strange question to consider when you're doing a chemistry class, but can you think about what's the difference there? Like, intramural sports are ones that are within your own school. Like a lot of colleges will have, intramural soccer, which means that maybe at Penn State, teams of students who go to Penn State play against each other. And so it's within, and then mural means walls. If you have some Latin, and some of you guys do. But basically it means within the walls, within your own school. Like, we've had an ultimate frisbee tournament. I know we used to have a badminton tournament at Dallastown. There's the dance contest in gym class. Those would be intramural activities where they are like just with students within our own school. Inter is a prefix that more or less means between in Latin. And scholastic means schools, and this is sports that are played between neighboring schools, like when Dallastown plays Red Lion in basketball or football. So why do I bring that up? Well, intra means within and inter between. And one of the things you're responsible for in this unit is knowing the difference between intramolecular forces and intermolecular forces. Okay. And the big difference is, of course, in that prefix right there, intra or inter. And intramolecular forces within the particle or molecule. You learned all about intramolecular forces in part A of the course. Like, for example, water molecule has an oxygen, which has, the 6 electrons. And then there are hydrogen atoms that share electrons with the single electrons on the oxygen. And we've got a water molecule. And this right here, where the H is bonded to the O, where H bonds to the O, those right there, that is an intramolecular force. It's holding the particle or the molecule together. It's within the molecule. But we also have learned this year how water can tend to be polar. Okay. You learned that in part A of the course as well, how oxygen has a higher electronegativity and the electrons go towards the oxygen, which makes this side of the molecule negative, and then these hydrogens, this side over here, is positive. And so as a result, water molecules can be attracted to each other. If I have, oh goodness, you'll see that happen every once in a while to me. So if I have a molecule of water and it's negative on this end and positive on this end, now it's neutral overall, but the charge is not distributed equally. Remember, the one end is negative, the other is positive. We call that a polar molecule. If it's near another water molecule, oh goodness, this is not going to be my day for this, huh? So if it's near another water molecule, then the positive on the one molecule can be attracted to the negative on the neighboring molecule. That is an intermolecular force of attraction, and it's between neighboring molecules. Now, sometimes molecules just have really small intermolecular forces of attraction. Maybe they're due to something that's temporary. That would be sort of like, if you've ever walked across the carpet in your slippers and got a temporary charge, static. It's pretty weak force of attraction. And that can be the same thing with molecules. Then there's where they're permanently charged on, the one end or the other. They're polar. That can depend on how big the electronegativity difference is here between these atoms. When you have hydrogen bonded to an atom like oxygen with a really high electronegativity, it's a big difference. And then this attraction is strong because this hydrogen is just like an exposed proton. So it depends. And, you can have other ones like HBr. That molecule looks like this. The bromine has a higher electronegativity, so this end's negative and the hydrogen end's positive. But this is not as polar as water. So while a neighboring HBr is going to be attracted because, this end's positive and it's going to be attracted to the negative of the neighboring end. This attraction is right here between HBr and HBr is going to be weaker than this one. So, there's varying strengths. There's some intermolecular attractions that are just temporary. There are others like this and this that they are permanently polar molecules and the attraction is not just temporary. However, sometimes it's weaker, other times it's stronger, like water attracted to a neighboring water molecule. So I did want you to know there are different strengths of intermolecular attractions. Some are weaker, some are stronger. And so in this lesson, you're going to learn the difference between the intra and intermolecular forces, which kinds of particles attract one another. We already kind of started talking about that. The polars are attracted to other polar molecules. Then we'll talk about how does that affect whether something is a solid, liquid, gas, and then this is a theory that describes gases, and then we'll deal with gas pressure units. Okay, so there's a couple different things. So which kinds of molecules or what kind of particles or molecules are attracted to each other? We know that polar molecules are attracted to other polar molecules, okay? So for example, like the, it's just so hard to see. Let me get something that's a little lighter. So this, like for example, that HBr that we had, okay, it's polar, and obviously it'll be attracted to neighboring HBr molecules, but it's also going to be attracted to a water molecule. I mean, they don't have to be the same molecules to attract each other. The hydrogen's positive, the bromine's negative. And what's going to happen there is that there will be attraction between these neighboring molecules. Okay. So polar molecules are attracted to other polar molecules. Like, you know how sugar dissolves in water? That's because sugar is polar. The structure is way too complex for me to draw right here. But sugar is polar and it's attracted to water. It dissolves in water because they are attracted to one another. Polar molecules are also attracted to ions. So let's say I have my molecule of water, okay? And remember the hydrogen ends are positive and the oxygen end is negative. And let's say I have something like sodium chloride, which is salt. If I put sodium chloride in water, it's going to break apart. The sodium ion is going to be attracted to the negative end of the water, and the chloride ion is going to be attracted to the positive end of water. And so that's like an ion dipole attraction there. The more polar the molecule in the middle is, like the more polar the solvent is, the better it is at attracting and dissolving ionic compounds. And that's why they often refer to water as that universal solvent. I know they talk about that in biology. But there are some ionics that do not dissolve in water. And sometimes the positive and negative ion, they're attracted to each other so strongly that the water can't pull them apart from each other and break up their crystal lattice and dissolve them. So ions are attracted to water, but sometimes they're more attracted to each other and they don't dissolve. Okay, so there are some things that dissolve very well in water and others that barely dissolve. Now, one thing polar molecules are not attracted to is nonpolar molecules. Like if I have something that is nonpolar. For example, like, carbon dioxide, symmetrical structure. I don't know if you remember, that makes it nonpolar. It is not soluble in water, which is polar. Oil is nonpolar. It is not soluble in water. They're just not attracted to each other. And anything that is nonpolar doesn't have positive and negative ends. So, it is just not attracted to the water, and the water would rather hang out with itself since it's not attracted to these nonpolar molecules. So, some vocab words for you. Okay. This, miscible, this means that something is, able to be mixed. Okay. Polar molecules are miscible with other polar molecules and lots of ionic things. Non-polars, they'll dissolve with other non-polars. Okay. Like if I have two things that are non-polar, they're not really attracted to each other, but there's nothing opposing that attraction either. So just the fact that molecules are constantly, moving, they will mix with each other. But then here's another vocab word, immiscible. And that means that they are unable to be mixed. Polar molecules are immiscible with nonpolar, like oil and water do not mix. If you've ever seen salad dressing, that's oil and vinegar, okay, you can probably guess from this without even knowing what the structure of vinegar is like. Since the oil is nonpolar and these are immiscible, they do not mix, that means the vinegar is polar. And, if you ever see the structure of, the acetic acid molecule, you can see that it's, there's no symmetry here. That's a hydrogen down there. It's not symmetrical, right? So it's highly polar. So vinegar will dissolve with water. Okay, this will mix with water because they're both polar. It is miscible in water. But vinegar will not mix with oil because the one is polar and the other one is nonpolar. So they are immiscible. You might wonder, sometimes in class, I like to talk a little bit about, what about soap? Soap is kind of cool. Soap is like this really, I'm having trouble. I need a fatter eraser to kind of erase a little faster. But soap is like a really long molecule. And the soap has like this really long non-polar end that's attracted to the oil. Well, it's not really attracted to it, but it'll mix with it. And then on this end, it has, I think it is a double bond O and like OH, something like that. And it is polar on the one end. And so it's attracted to the water on the one end, and it's attracted to the oil on the other end, or it'll mix with the oil on the other end. And the result is that it's pretty cool. Soap can kind of bridge the gap between oil and water and helps the water break up the oily dirt that, is on skin and clothing and dishes and stuff and sort of whisk it away. So that's how soap bridges the gap between the water and the oil. It's got one end that's polar and one that's nonpolar. Now, what does all this have to do with solids, liquids, and gases? Well, if particles have a really strong attraction for each other, they will stay close together and be in the solid phase. All particles have some energy of motion, kinetic energy. Even if they're in the solid phase, the particles can be like kind of vibrating in their fixed positions. But at room temperature, which is 25 degrees Celsius, if If the attraction between the neighboring particles is strong enough, the kinetic energy can't overcome it, and that substance will be a solid at room temperature. If the substance is a liquid at room temperature, that means, again, that there's more attraction than the kinetic energy at 25 Celsius, just isn't enough to overcome the attraction between the neighboring particles. Sometimes the particles near the surface, they have enough kinetic energy, they can escape from the surface. But, like with water, it doesn't happen that fast, right? The less attraction there is between the particles, the faster something evaporates, like hand sanitizer. Okay. And if there's very little attraction between the particles, like, for example, carbon dioxide is nonpolar, there's very little attraction between neighboring particles. Nitrogen, do you remember doing these? Is nonpolar, very little attraction. If there's very little attraction between the neighboring particles, then they end up with a lot of space between them because there's nothing, boy, that looks like small. That's supposed to say space, but there's nothing to hold them together. And so when there's very little attraction between the neighboring particles, even at something as low as 25 degrees Celsius, they have enough kinetic energy to like zip around and speed away from each other and not stick together and have, I had to try and do it again and do it better, have space between them. And as a result, then they are gases at room temperature. And that's what this next little part of this presentation is about, is, what makes something, behave like a gas? What makes it a gas? And it is that they are spaced far apart in comparison to their own size, and they move around rapidly in straight lines. Now, if they bump into each other, then they might, like kind of like pool balls on a table. They bump into each other and they might be deflected off into a different direction, but they keep moving. And you have random motion where they run into each other in the walls of the container and just keep bouncing around. Why do they behave like that? Because they don't have forces of attraction between the neighboring molecules. Even if they have little temporary electrostatic forces of attraction, those are pretty weak. Like back to that example where I said about walking across the carpet with your slippers, and your hair gets all electrostatic. You can't hold the pillow, the corduroy pillow, 10 feet away and have your hair stand up to meet it. They got to get close to each other, right? Well, these particles have enough space between them and they're moving fast enough. Even if they did have a teeny weeny little bit of attraction, it's not strong enough to hold them together. And so if they do bump into each other, they just bounce right off of one another and keep going. They call that an elastic collision where they don't lose any energy. Now, particles, because they're moving around, if they're inside of a container, like if I have a jar or a box with a lid and I've got particles in here zipping around, when they bounce off the walls of the container, they actually will apply a pressure to that container. When they're moving and they hit the walls of the container, that applies a force. And then whatever the area is of the inside of the container, okay, it's the collective force of all these little particles bumping into the walls. And then that force is divided by the surface area inside the container, and you get the pressure. Okay. Now, one of the things I do if we're in class, you stand up and stand on your 2 feet. You feel pressure on your feet, right? The force is your body weight. Okay. And that force is being applied over the area of, the feet on the ground, right? And that area would be like in square feet, the dimensions. I know our feet aren't perfect circles or ovals or squares or rectangles or anything, but area is in like length times width or like some sort of square feet. So you may have heard of a pressure unit before that is called PSI. Maybe you've inflated a car tire or a bicycle tire or a basketball or a soccer ball or something. But if you do pounds and then it's square inches, okay, that they call PSI, pounds per square inch. That's a unit of pressure, okay? Now, the unit of pressure that we use in chemistry a lot is called the millimeter of mercury. And that's because Evangelista Torricelli, hundreds of years ago, figured out how to measure air pressure in an instrument that he called a barometer. Now, excuse me, barometers today don't have mercury in them. Like this dish is filled with mercury, and this is mercury inside of this tube. Barometers today, they have like vacuum chambers and digital readouts and everything. But hundreds of years ago, Torricelli took this tube. I don't know if you ever took something and like he totally filled it like to the tippy top with the mercury and you put your finger over it. Did you ever do that in the bathtub? And then you turn it upside down. And so he puts it upside down in this vat of mercury and the mercury level falls. It doesn't stay all the way to the top. And so this area inside here, this area at the top, okay, is this right here and here. This is a vacuum. There's nothing in there, okay? And what he noticed was that the height of the mercury would change depending on the weather or the day. And see, the weight pushing down inside, distributed over this area, creates a pressure. And if the level is not moving, that means the air pressure pushing out here and the weight of the mercury pushing right here, they're creating equal pressures. So he could measure how much is the air pressure by how tall this mercury column was. On a day where, the air pressure was lower, this mercury column would fall and not be quite as tall. Maybe it would come down to here. And then on a day where the air pressure is higher, it'd be pushing harder. So kind of pushes some of the mercury up in here until the weight of the mercury over this area is equal. And now it's at a higher level. He found that he could measure air pressure by how tall the mercury column was. And he found that normal air pressure was almost 30 inches tall for the mercury column, which is an equivalent of 76 centimeters. So that's where we kind of got standard air pressure, okay, 760 millimeters of mercury. And sometimes we call that 760 torr in honor of Torricelli. Since that is typical air pressure, then we call that an atmosphere. Now, PSI, here's the PSI. Typical air pressure in PSI is 14.7 pounds per square inch. So if you took like an inch square on your arm, there is 14.7 pounds of air pressing on that square inch. That's all over your body. Every square inch has 14.7 pounds of air, pressing on it. Okay. This one, this pounds per square inch, while we use it the most for our car tires, which might be something like 30 psi. If you ever go to Sheets and put air in your tire and you're punching that number up or down to what your tire, because different tires and different weight vehicles need different pressure in the tires. Yours might need 32 or 30. That unit that's on that Sheets, pressure gauge, that's in PSI, pounds per square inch. We don't use those a lot in chem, but the ones that we use are right here. And the Pascal, do you remember from ninth grade science, instead of pounds, you use newtons for a force? And then instead of measuring the area in square inches, if they measure it in square meters, a Newton per meter squared is a Pascal. This is such a big number, though, that then they use that metric prefix kilo. There's 1,000 pascals in a kilopascal. So divide Pascal by 1,000 and you get 101.325. So these are the ones, I'm going to put a blue star. This one, this one, this one, and this one. These four, those are the four that you're going to use most often. And, you can come back to this all throughout these screencast presentations. You can stop and take notes. You can rewind. You can watch them again. But you're going to need these numbers to do some problems. And the problems that you're going to do are going to look something like this, like where we need to convert sometimes from one pressure unit to another. And what we want to do is use factor label. So remember, in factor label, you start with the given number and you set up a factor, and the top and the bottom of the factor have to be equal. So we go back here. We know that 1 atmosphere is equal to 760 millimeters of mercury. Okay, so I'm going to put the millimeters of mercury on the bottom and the atmosphere on the top. You just kind of finished practicing that with stoichiometry, how you want the label that's here to be the label on the bottom so that it divides out. And then your answer has the label that you want. And then to solve this, you have to take 895 divided by 760. And I'm going to round it to 3 sig figs. I got 1.18. So 895 millimeters mercury is equal to 1.18 atmospheres. Okay. So now we have our answer there. Let's try another one. 89.5 kilopascals. Okay, and we want to convert to torr. So we got to put the kilopascals on the bottom, torr on the top. If you need to go back, you can. I don't really want to go back though, because it's going to take everything off of here. That 760 torr is equal to 101.325 kilopascal. So the top and the bottom are equal. I did not mean to erase those. The kilopascals divide out. The torr did not divide out. That line just randomly went through there when I made my check mark. To get my answer, I have to take 89.5, divide by the 101.325, and multiply by the 760. And I got, 671 torr. So 671 torr. You're going to need these skills in a future unit. So I'd like you to practice these, okay? And you can pause this presentation right here and try these on paper. And then when you are done, you can restart it and you'll see me solve them. So go ahead and pause. Okay, to go from millimeters mercury to atmospheres, we got to have the millimeters of mercury on the bottom. It's 1 atmosphere is equal to 760 millimeters of mercury. So the millimeters of mercury divide out. My answer will be in atmospheres. 675 divided by 760 is 0.888. So 0.888. That's how many atmospheres. Now, the second one, you had to go from atmospheres to kilopascals. So we want to get rid of atmospheres and we want to get kilopascals. And it's 1 atmosphere is equal to 101.325 kilopascals. So 0.75 times 101.325, and then of course divide by 1. And I got 76 kilopascals. I'm just doing the same things. So hopefully that's what you got. We talked about the difference between intra and intermolecular, within versus between neighboring particles. We talked about which kinds attract one another, like polar is attracted to polar, polars are attracted to ions. Nonpolar will mix with nonpolar, but boy, the polar and the nonpolar, they do not mix. And ions are not going to mix with nonpolar. Like salt does not mix with oil. Then it says list the postulates of the kinetic molecular theory, how gases are spread far apart in comparison to their own size. They move rapidly in a straight line until they have a collision and then bounce off randomly. They do not have strong forces between them. They really pretty much have no forces of attraction between them. And then if they do bump into each other, they just bounce off of one another without losing any of their energy. And then at the end, you learned how to convert gas pressure units. Okay. So hopefully, you got those things out of this, and anytime you can go back through and review or practice or stop or take notes on parts of this presentation, and practice the Quizlet to see how well you know these things.